It's up front here. I was in the back yesterday, and I realized that some of the transparency can't be seen so well. So, Kome, why don't you come way up front, and Nick, and there's lots of space up here, and you can actually see the transparencies. So, so this conference provides a bridge between sort of computational methods and geometry, and yesterday we heard about topology, differential geometry. So this talk is going to make a connection to algebraic geometry. So, and of course, this is going to be tropical algebraic geometry. So this talk will have 3 parts, roughly of equal length. In the first one, I will tell you about tropical hypersurfaces, in particular tropical curves in the plane, in a fairly elementary way. So here in green, you have something called an elliptic curve. That's an example of a cubic curve in the plane. Then the second part will be a little bit rougher going. I'll actually give you the official definition of a tropical algebraic variety. So that's going to be more technical. And then finally, in the third part, I'm going to talk about linear spaces, and then the parameter space of all linear spaces, which is the Grassmannian. There are 2 papers on the archive that most of this material is contained in. So yesterday we saw the tropical semiring, the real numbers with the tropical addition, which is the minimum of 2 numbers, tropical multiplication, which is the sum of 2 numbers. So then we're ready to form polynomials. So as soon as we can add and multiply, we can form polynomials. So a tropical polynomial is a tropical sum of R monomials. What's a monomial? So that's Ci, a constant, times, tropical monomial. And if you think about it for a moment, a tropical monomial is a linear function, a affine linear function, and therefore a tropical polynomial. Remember, addition is the minimum. A tropical polynomial is given as the minimum of R affine linear functions. So if you think about tropical polynomial as a function from R to the n to R, well, all these times become a plus in ordinary arithmetic. The plus becomes a min. So this is the minimum of R affine linear functions in n unknowns, and that is then a piecewise linear concave function. So I always get concave and convex mixed up, but I think this is a concave function.
Sorry, is it assumed that the exponents are integers?
Yes, let's assume that the exponents are integers. So in this talk, the Ci are real numbers, possibly including plus infinity, and the Aij's are integers. Let them be integer, possibly negative. Doesn't really matter. Maybe positive integers. Okay, so then the tropical hypersurface defined by this polynomial is the set of all points in R to the n, x1 up to xn, at which this piecewise linear function is not differentiable. And another way of saying that, at which it's not linear. And yet another way of saying that, that's the set of all points x such that this minimum over R things is attained at least twice. Okay, so I'm interested in all those points x such that there are 2 indices, and this maybe should be I from 1 up to R, and got scolded yesterday by Jeff, so I didn't bring my marker, so this n is probably an R. So among these things from I from 1 up to R, there should be 2 indices, I and I twiddle, such that 2 of them are the same and less or equal to every other thing. Okay, so let's start our discussion of algebraic geometry. Thank you very much. Okay. Okay, there we go. So this n is an R. Great. Okay, so let's talk about lines in the plane, the very beginning of algebraic geometry. So line in the plane is given by a linear polynomial in 2 unknowns, x and y, so ax plus by plus c. Now evaluating this function f, in ordinary arithmetic, it's just the minimum of a plus x, b plus y, and the constant c. So we're interested in all those points in the plane where this minimum is attained twice. Well, there's sort of three cases, right? Either the first two things are equal and less or equal to the third. That's a little southwestern half ray. And then by symmetry, you know, there's the northern half ray and the eastern half ray. And there's sort of a very special point in the middle, c minus a, c minus b. That's the unique point in the plane at which the minimum is attained thrice. Okay, so lines in the plane are parallel translates of these little tripods, consisting of a northern half ray, an eastern half ray, and a southwestern half ray. So what about these? Well, any two lines in the plane meet in a unique point. So if you draw two lines, a red line and a green line in the plane, then they will meet in a unique point. Okay, well, you could argue that there are degenerate positions, and I'll talk about these degenerate situations in a moment, but let's say you draw two general lines in the plane. They always meet in a unique blue intersection point. Converse, for the polar statement, if you draw any 2 points in the plane, say the green point and the blue point in the lower left picture, then there will be a unique line incident to those 2 points. So we should maybe observe that. So that's kind of the beginning of a pretty good geometry. Two lines meet in a point, 2 points determine a line. And perhaps we can move on to quadratic curves. Quadratic curves are given by a polynomial of degree 2, ax squared, bxy, cy squared, dx plus ey plus a constant f. And then the tropical curve, there are several combinatorial types, and these are two possibilities. So a quadratic curve in the plane will be an embedded graph that has two parallel northern half rays, two parallel southwestern half rays, and two parallel eastern half rays, 2 being the degree of the quadratic curve. And otherwise, we have exactly what happens in Eric's first talk. It's an embedded graph that satisfies the zero tension condition. Okay? So a quadratic curve in the plane is a curve with the asymptotic behavior, and we have integral lattice zero tension at each node in the middle. Very good. Two lines always meet in a point. What about two quadratic curves? What would happen if I intersect these two quadratic curves in the plane? And it turns out they always meet in 4 points. So any two quadratic curves meet in 4 points. That's Bezout's theorem. In general, Bezout's theorem stipulates that if we have two general curves of degrees m and n in the plane, then the expected number of intersection points is the product of the degrees, m times n. And indeed, here we can see that the green curve meets the red curve in 1, 2, 3, 4 points. Now, there are situations where we have to take multiplicity into consideration, and that can be formulated conveniently with the zero tension condition as well. But basically, any two quadratic curves meet in 4 points. So Bezout's theorem holds for curves, and it holds for complete intersections, say 3 surfaces in 3 space, etc., etc. Bezout's theorem was proved in 1790. There's a more recent version, lots more practical in application, from about 25 years ago, called Bernstein's theorem. Bernstein's theorem says if you have a system of n polynomial equations in n unknowns, and the system is sparse in the sense that only few of the terms occur, then the expected number of complex roots is the mixed volume of the Newton polytope, and that holds as well. In fact, if you think about it for a moment, well, this is in fact, in my view, the best proof of Bernstein's theorem, is to first prove it tropically and then deduce it in ordinary algebraic geometry. There's been some spectacular work recently by Mikalkin, who showed that Gromov-Witten invariance in the plane can be computed tropically, but that I think would take us a little far in this workshop. So let's just note that Bézout's theorem holds 2 quadratic curves always meet in 4 points. Now, what about degenerate situations? Well, in ordinary geometry, if you have 2 quadratic curves, let's say over the complex numbers. So unless they sort of share a component or identical, they will meet in 4 points, but there are sort of complicated issues of multiplicity and monodromy. And it turns out that all evaporates in tropical geometry. So in the paper that I quoted with Theobald and Richter-Gebert, there's a corollary, 4.4, that says any 2 curves of degree C and D in the tropical projective plane intersect stably in a well-defined set of C times D points, counting multiplicity. Even if the curves are very, 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 very degenerate, they always meet in C times D points, well-specified points. So let's see an example. So here in black, this might be hard to see in the last row, so I'd like to extend again an invitation to join the first row. So if you were in the first row, then you would recognize the black thing as a tropical line intersecting the green quadratic curve. And here they are in fairly general position, and they meet in 2 points, A and B. So a line meets a quadric in 2 points. But now let's progressively move this intersection from general position to more special position. So for instance, in the second picture, the line got pushed down, and it shares sort of an ordinary line segment with the curve. But still, there's sort of 2 distinguished points, A and B. So just observe what happened to the points A and B before. They will sort of walk down here. They will move down to these points A and B. And that intersection is stable in the sense that if you wiggle off again from the lower middle picture, then A and B, the unique intersection points, will be in the neighborhood. And here's the sort of the most degenerate situation. We even push the line a little bit to the right, so there's a lot of coincidence here, and still the stable intersection A and B is well defined. So the self-intersection of a line with itself is the point. Okay, so every line meets itself in a unique point, a well-defined point, and same, every quadratic curve meets itself in 4 well-defined points. And these are the 4 nodes at which the tension takes place. So here, let's observe this. So this is to visualize the stable intersection of a conic with itself. So let's move it off itself. So there are 4 well-defined intersection points. Then we progressively move one of the quadrics onto the other. And in the limit, we get the 4 special points. And that's a very well-defined stable situation. And sort of summary is this: in tropical geometry, there's no monodromy. Okay. What else? Maybe this is a moment to pause for a question.
How do you find those points? I mean, how do you define? Why are they well defined?
Well, so that's the theorem. So the corollary says they are well defined. So if you have any, let me be precise. So if you have any 2 curves, regardless how special they are, there exists a well-defined set of C times D points, such that for any movement in a neighborhood, the generic intersection points are what they are supposed to be. And you can't do that in ordinary geometry. If you have a line lying on top of itself, well, then there's no such thing. Is this clear? Yes.
So monodromy happens when you have some sort of special intersection. You're moving through generic intersection and loop around there.
Mm-hmm.
And I guess you can't do that here because you don't have like a complex plane to move around. Is that what's? When I think of monodromy, I think of sort of moving through the generic things around loop around something that's special.
Okay, maybe.
Maybe it's advanced, you don't know.
the answer is maybe. David?
What you're saying must have a few more caveats. But if you take the very special line, which is just x equals y, and you just take that on itself, there's no particular interesting forecast.
I agree. Okay? But that is not a curve of degree 1. So if you actually read our paper, then you would know that that special... Just kidding. So, no, it's the other paper. It's the other paper. But that's actually not allowed as a curve of degree 1. So curve of degree D is one that has the correct Newton polygon. So I think this corollary holds up so far, but let's see.
Is there a simple example where you can see multiplicities?
Yes. So let's do an example. So let me, drag and click. So I'm going to click on this green curve now, and I move it to the left in such a way that this northeastern line segment meets this green northwestern line segment, that they would form a point of multiplicity 2. So that's the determinant of the primitive vectors in that direction. So if you have a vector like this and a vector like that, so they would have a point of multiplicity 2.
Were you saying that when the curve intersects itself at the appropriate number of points, that it is, I'm missing something about quite what that means. Is there something about multiplicity?
Yes, but I don't want to go into it. So it's basically there's a lattice index, and that has to be taken into consideration.
So yesterday, to do convexity, you were basically doing this in a projective space, and you had to mod out the multiples of 1, 1, 1, 1.
Same here.
Same has happened here, basically.
Could happen. So if we do the line, here I drew it in the affine plane, but in fact it's more convenient to write c times z and then do it in the projective plane.
I'm just wondering why you're not losing anything at infinity.
There is no infinity. The tropical projective plane has no infinity. That's why it's easier. See, that's why it's so much easier. Okay, so in Cinderella, which if I were smarter with computers, there would be a live demonstration of the beginnings of tropical Cinderella. So you can... Question? No. It's not compact. Okay, so we click on the screen, and there are 5 points, A, B, C, D, and E. And then, lo and behold, there's a unique quadratic curve passing through those 5 points. Any 5 points in the plane. Certainly that's true generically, but it's also true for 5 special points stably. So if you draw any 5 points, and that's why Cinderella works. That's a good thing for computational geometry, because now you can drag and move A, B, C, D, and E around, and by the stability, Cinderella works very well, even in degenerate position. So how do we calculate this? The curve of 4 points, through the quadratic curve through 5 points in the plane, can be written as a 6 by 6 determinant, where you write down the homogeneous coordinates of the points and together with their quadratic images in the first 5 rows. Now here I've written this in ordinary arithmetic, okay? And then the last row is the corresponding thing for an indeterminate point, x, y, again written in ordinary arithmetic. And then the tropical determinant of this 6 by 6 matrix is the piecewise-linear function whose curve is the green curve. Maybe a few words about tropical determinants. They're easy to compute. That's the polynomial time algorithm for the assignment problem. So let's look for a simple example. So the tropical determinant of a 3 by 3 matrix, you just, in ordinary arithmetic, well, in tropical algebra, the permanent equals the determinant, of course. So the tropical determinant equal the tropical permanent is the minimum of, these 6 terms, a plus e plus I, dot, 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 c plus e plus g. Of course, so in general, they're n factorial terms. Then this tropical polynomial, like all tropical polynomials, determines a hypersurface, namely the set of all matrices for which this minimum is attained twice. That's in the 9-dimensional space of all matrices. And you can observe that this happens if and only if the 3 points given by the rows of this matrix lie on a common line in the projective plane. So tropical determinants and tropical linear algebra make sense and have essentially the same relations to projective geometry as they do in the ordinary case. And as I said, the tropical determinant, of course, of an n times n matrix, you don't have to evaluate n plus n factorial sums, but this is an assignment problem, and Hungarian method, I guess, we'll do it very fast. Okay, not everything is as nice in tropical geometry, and this was actually a result we're very, very proud of. Pappus' theorem is false, so we worked very hard to try to prove Pappus' theorem, and there's a counterexample, actually. So Pappus' theorem here is the line version. There are 9 lines, A prime, A double prime, B prime, B double prime, C prime, C double prime. And there are 8 intersection points labeled 1 up to 8. And then the statement of the theorem is that there's also a 9th intersection point, number 9, circled in green. And then down here is a non-Pappus configuration. It takes a little practice to unravel this picture, and it's impossible if you're in the last row. So there are 9 lines in the plane, again labeled A prime, A double prime, and so on. And the first 8 intersection points are okay, but then these lines, this, and this, they're supposed to meet in a point, but they don't. So the incidence version of Pappus' theorem does not hold. Question?
So this means that there's some kind of lack of commutativity, I think, but I'm a little unclear in what way.
Maybe associativity? Yeah, I don't know. It'd be interesting.
What happens? So the generalization is to cubic curves. So you take 2 cubic curves.
You want to stand up and
no. What I'm wondering is, this sort of question is, but something like, so you take 2 cubic curves. You pick 8 points. They have to meet a 9th point.
Yes. So
I guess you
so Poncelet's theorem is a generalization of Pascal's theorem and is therefore also false in this version.
You don't have association.
However, so the good news is we think that there is a version of Pappus' theorem that is true, and that's a conjecture. We are not able to prove that. So you can formulate, so Pappus, any of these incidence theorems, you can formulate them as an incidence version or as a construction version. You can say, you start with some small free configuration, and then you construct another point, you construct another line, and you specify a construction sequence. And then as you follow the construction sequence, something is going to happen in the end, and we believe that that version should actually be true, and that's a conjecture, and it would be fantastic if somebody could get interested in it. And of course, all of these things were drawn and done with Cinderella, which we all love so much. Okay, so this is the end of the first talk. It's the definition of tropical hypersurfaces, the elementary definition of tropical hypersurfaces. And we've seen that many, many things from ordinary geometry hold here. In fact, are even easier and better, but some things don't hold. So we have to be quite careful in generalizing too quickly. Okay, so now comes the second part with the general definition of a tropical variety. And I have to say a little bit of algebra to define this. Okay. So this is ideals, variety, and algorithms. So my interest in mathematics is primarily to solve systems of polynomial equations. And here, in this context, we like to solve them over a field like the field of Puiseux series. So K is the field of Puiseux series. So these are power series, formal power series with complex coefficients in a variable t. The exponents are rational numbers. They're allowed to be rational numbers. And the requirement is that the rational numbers that appear have a common denominator and have a lowest element. So they have to start somewhere, right? So something t to the minus 17 over 3 plus higher order terms would be a Puiseux series. here in real algebraic geometry and computational geometry, you could actually replace, for most of what I say, you can replace c by the real numbers r, and you can replace t by epsilon. So think of t as a small number epsilon, and think of c as the real numbers. So such a field element has an order. So there's a valuation from k star, the non-zero elements, into the rational numbers. It simply takes such a series and records the lowest appearing exponent. So with that said, every honest polynomial, so we like to solve systems of polynomial equations in n unknowns, x1 up to xn, with coefficients in k. So we have these coefficients, but these coefficients will depend on a parameter, t or epsilon. So a polynomial will look like this. It's a linear combination of monomials, and each coefficient will be a scalar, but that scalar is sort of a funny series in t. I should have said this is an algebraically closed field. That's why we like it, and the R epsilon version is a real closed field, so almost as good as an algebraically closed field. Now, every polynomial that comes our way has an associated tropical polynomial. And it's the same polynomial. Just write down the same polynomial, except for these complicated coefficients, you just record the order. Yeah? So you take a polynomial, and the tropicalization is the same polynomial, except before you had some, coefficient ci that's a function of t. You just write down the order. Okay? That's the associated tropical polynomial. Now, tropical polynomials are piecewise linear functions, so there's another way of saying the same thing. Namely, if you have a vector w in R to the n, well, that gives a weight to each polynomial. So the weight of a variable xi is wi. The weight of a monomial, is the sum of the weights of the variables, and so on. So the initial form, so one way of saying what the piecewise linear function f is, it's simply the function that eats a weight vector and produces the weight of the polynomial. So then, if we're given these weights, there's an initial form, which is the subsum of all terms of lowest weight. I'll denote that by in w of f. Okay, example. So suppose we have a polynomial in two variables, x and y, and these things in the parentheses, these are the coefficients. So this is a polynomial in x and y with coefficients in our field t. Then the corresponding tropicalization is this tropical polynomial. So it's the same monomials, and whenever you had a coefficient before, say square root of t plus 3t to the 7th, then you simply write down the order. Okay? So big F is the tropicalization of the honest polynomial little f. Here's an example of an initial form. So if we take the weights 1, 1, then we can calculate the weight of our polynomial. So this is 3.5, right? So f evaluated at 1, 1 is 3.5. And then the initial form is the sum of all terms of weight 3.5. So this one has weight 3.5. This one has weight 3.5. But finally, back there, this has weight 4. So 8 times y to the 4th gets erased when passing to the initial form. Okay. Now, of course, we don't want to solve just one polynomial in n variables. We've done that in the first part of the talk. We want to solve many polynomials at the same time, so we have to organize them in an ideal. So I is an ideal in the polynomial ring in n variables x1 up to xn, coefficients in k. And if we have some weights w, then we have the initial ideal. So the initial ideal of I is the ideal generated by all initial forms where f runs over all polynomials in the ideal. And then this defines a natural polyhedral cell decomposition of R to the n into finitely many closed, convex polyhedra, relatively open convex polyhedra. Namely, W and W twiddle are in the same cell of this so-called Grobner complex if they give the same initial ideal. Okay, so we're fixing an ideal. We're fixing a system of polynomial equations. You give me some weights W. Well, that produces an initial ideal by, I don't know, Maple, Macaulay 2, any of these. And then, you know, if you give me a W and you give me a W tilde, then they are equivalent. They lie in the same cell if the answer is the same. And that gives a decomposition of R to the n into polyhedra, convex polyhedra, and that's called the Grobner complex. Okay, so here's the theorem that defines tropical algebraic variety. So suppose we're given a system of polynomial equations in n unknowns, x1 up to xn with coefficients in k. Then I'm going to define a subset of R to the n, called its tropical variety, in three possible ways. The theorem is that they're the same. A, we look at the honest variety over the algebraically closed field K. So V of I is the honest, old-fashioned, ordinary zero set of I over K. K is an algebraically closed field, except we have to take K star. So we're going to look at only those points, all of whose coordinates are non-zero. So you look at the honest variety, V of I, and then you just take the order of every point. So a point on this variety will be, you know, scalar, scalar, you know, coordinate, 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 coordinate. And every coordinate will be something that depends on t. And, you know, just coordinate-wise, you take the order. And you do that for each and every point on the variety. You get, you know, a bunch of points in R to the n. Well, actually, the way I set it up, they all have rational coordinates. So I'm going to take the closure. It's really just, you know, convention. People think of the real numbers as easier than the rational numbers. And so we'll just take the closure. But you could erase closure if R were Q. So we just take the set of all orders of all points and the old-fashioned variety, and then you just close it up. That's a subset of R to the n. B, the set of all weight vectors W such that the initial ideal contains no monomial. Contains no monomial. Okay? Well, if W is a general weight vector, if you give general weights, then the initial, you know, term will be a monomial, right? If you W1, W2 are chosen at random and you have a polynomial, then there's, you know, all the terms will have different weight and the lowest term will be a monomial. So such a W is bad. So we want those very, very special W's that for each and every polynomial in our system selects more than one monomial as its lowest term. So, for instance, this W would be a good W for little f, right? Because it picks a leading more than a monomial for its leading terms. So the set of all weight vectors such that the initial ideal is monomial free. And finally, if you enjoyed the first part of the talk, then you simply intersect all the pictures that you've seen before. So take every polynomial little f in the ideal, tropicalize it. So pass from little f to big F. Compute the tropical variety using the rule I described. Minimum is attained twice. Draw it in R to the n. Do it again. And do this for every polynomial in the ideal. Each and every of the infinitely many polynomials in the ideal. Intersect all the pictures. That's a subset of R to the n. And the theorem is that these three coincide. So this common set, A equals B equals C, is a polyhedral complex. It's a union of finitely many closed convex polyhedra, some bounded, some unbounded. And that's called the tropical variety of the ideal I. And it turns out that here you can actually replace this infinite set I by an a priori finite set called the universal Grobner basis, and that's a consequence of B. So we can actually compute these things. So there are algorithms, and maybe not terribly efficient at the moment, but in principle, all of these things can be computed. Okay. Here's some corollary. Now suppose you're given a system of polynomial equations, none of the coefficients where none of the coefficients involves a t at all. That's legal, right? I could guess some equations, and, all the coefficients are actually complex numbers or real numbers. There's no t. It doesn't depend on t at all. In that case, the tropical variety, tau of I, is a fan. So a fan is a finite union of convex polyhedral cones emanating from the origin and fitting together nicely. So this is the situation if there are no t's inside. And this fan, this was sort of the historically, as far as I know, the first occurrence of tropical algebraic varieties is a work of George Bergman from 1971. And he called that the logarithmic limit set of an algebraic variety. So the special case where the equations are over the ground field, there's no t at all, we get a fan, sometimes called the Bergman fan, or the logarithmic limit set. Now, if you have a polynomial, the coefficients of which don't depend on t at all, what are the coefficients of its tropicalization? Well, 0, 0, 0, 0, right? I mean, the order of a complex number doesn't depend on t, so the order is 0. So in this case, what this means, we're solving a system of tropical polynomial equations where each coefficient in each equation is 0. Okay? That's what we're doing. So these are systems of tropical polynomials, and every coefficient in every equation is 0. It's a very, very, very important special case, and as difficult as the general case, actually. Okay, what does the algebraic geometry buy us? Suppose I is a prime ideal, so of dimension d. Then the tropical variety is always a connected set. That's a non-trivial result. And it's pure of dimension d. So the dimension is equal to the dimension of the tropical variety. So that says, as a polyhedral complex, all maximal cells have the same dimension. They all have the same dimension d, and that dimension is the dimension in the sense of algebraic geometry. If you've ever been subjected to a course in commutative algebra or algebraic geometry, the definition of dimension is actually quite difficult. We sort of have an intuitive idea of what dimension is, but people have to go through some hoops to actually define dimension and say what they are. Now, if you believe, if you take as a primitive the dimension of a convex polyhedron, then this is another definition of dimension. Yeah? Suppose you want to know what's the definition of dimension of a prime ideal, or height. Well, it's the dimension of the set of all weight vectors such that the initial ideal is monomial free. Okay? So you can actually use this as a bad algorithm to compute the dimension. And so the dimension and pureness part was proved in a paper by Beery and Groves in the context of geometric group theory, the word problem that was alluded yesterday in Joel's talk is in this context. And then there's recent work by Einsiedler, Kapranov, Lind, and Ward that, among other things, has the connectivity statement. And then there's also a little bit about this. There's a different proof of this one in my book, Solving Systems of Polynomial Equations. Okay, there was a lot of theory, so let's reboot and do an example. Maybe let's do this. So let's see whether we can solve two ordinary linear equations and three unknowns. Okay, suppose we want to solve a system of two equations and three unknowns. X plus y plus z plus 1 equals 0. And x plus t plus y plus t squared z plus t cubed equals 0. So the x, y, and z are the unknowns, and the t's are the scalars. The t stuffs are the scalars. So we'd like to solve this for x, y, and z. Okay, we really want to do it. Okay, we want to solve this. Okay, so I claim, let's do it like this. So here's a point. So for instance, one solution point is the point x, y, z that has coordinates 2t plus t squared, then y coordinate -2, minus 2t, minus t squared, and z coordinate 1. So that you plug that in, and that's a point. Right? These are scalar, scalar, scalar. You plug it in there, it satisfies these two equations, so that's a point. Well, we take its order, so the order is 1, 0, 0. So therefore, the point 1, 0, 0 is a point on the tropical variety. Okay, so we found one point. Okay, let's find another point. So here's another point. T squared over 2 plus 2t. You should think of this as a power series. So this is a geometric, you expand this into a geometric series, then this is a power series that begins t squared plus higher order terms. So this has order 2, order 1, order 0. So 2, 1, 0 is another point. Okay, so we found 2 points. So we could go on and on and on and on and find 3 points, 4 points. We plot them in 3 space, and after a while we see many, many points. And then they all look like this. So the tropical line, and what I just did is the calculation according to description A. I looked at all the honest, ordinary, old-fashioned solutions on the variety, and I just calculated the order component-wise, and then I plotted that in 3 space. And there are these 2 special points. And then the tropical line, in this case, is a union of 5 one-dimensional pieces, 1 bounded segment between these 2 special points, and 4 unbounded half-rays emanating into the 4 coordinate directions in tropical projective 3 space. So in the plane, we had 3 directions, right? North, east, south, west. In 3 space, we have 4 directions. In 4 space, we have 5 directions, and so on. Okay, so the asymptotics of a line always has these half-rays going off in the coordinate directions, but then there's sort of a bounded part, and that's sort of the most interesting one, and is in fact the one we looked at yesterday. Okay, this is the end of the second part of the talk. So this is the general definition of tropical algebraic variety. And as a special case of this, by part C, of course, we see that if I is a principal ideal, we recover the tropical hypersurfaces that we had in the first part of the talk. Are there any questions?
Why is it called a logarithmic limit?
That's a very good question. So what you could do is, again, think of t as a very, very small number epsilon. And you can, rather than having this order map, you can simply do the following. So let's say this is the real numbers, or the complex numbers. And you can apply the logarithm coordinate-wise. So let's say you have a complex vector. And in each coordinate, you take the logarithm of the absolute value. And you plot that in 3 space. You're actually going to get a picture that looks like this. It's just going to be thicker. It's the so-called amoeba. There's something called the amoeba. You get a thickening of this picture. Okay? Well, I didn't tell you yet what the base of the logarithm is, right? So we could do log 2, or we can do log base 10, or log base e. But let's make the base bigger and bigger. Let's take the base to be 10, 100. Then the picture will change. And in the limit, you get this picture. This is actually one explanation. This is one way how you can get this as a limit. That's, in fact, cheating. That's not what Bergman did. But that's one answer. Nick?
Your definitions B and C both involve some minimum being obtained twice. Can you give some sort of motivation for why this is the right notion of vanishing?
This theorem works. Yeah. Well, if you plug in, if you have an honest point, then that's what's supposed to happen, right? I mean, if you take this thing and you plug it in there, in order for this to be actually a solution, the lowest power in t that appears amidst the expansion has to be attained twice. Jeff?
Remind me what V of I is.
Oh, that's the ordinary variety. So V of I is the set of all points with coordinates, non-zero coordinates in k, that are zeros of all the polynomials of I in I. So V of I is the... Yeah, so k star is the non-zero elements in the field k. So the n-dimensional algebraic torus. Okay. So I take V of I is simply the 0 set of the equations in I over the algebraically closed field k, except I rip out those points that have a 0 coordinate somewhere. Okay, Günther?
Do you know more about the topology of tropic varieties? I mean, about them being connected is interesting.
I would love to know more. So that's actually that's actually a problem in Bergman's original paper. Study the homology groups of these things. And I am very, 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 very interested to know more. Or homology, possible shellability properties. We know very little, and we'd love to know more.
You know something about plane curves already, about the loops and stuff.
That's right. So that's a good. Yeah, maybe we should put one. So here's one.
You had a cubic curve in your
Yeah. So Frank is referring to the cubic curve. So there you go. That's an elliptic curve. That's a curve of degree 3. So an elliptic curve is a curve of genus 1. That's a graph of genus 1. Okay. So in the plane, everything is easy and hunky-dory. I think really the problem is in higher dimensions. So in the plane, yes, everything is what you think it should be. Okay, so the third part of the talk, and that's partly an answer to sort of Günther's question, is let's talk about linear spaces in general, and then the Grassmannian, which parametrizes linear spaces. Let me define. So there's an example of a linear space. Let's keep it up for a little while. So let me define a tropical plane. So a tropical linear space, either in R to the n or in tropical projective space, is the tropical variety. And here I made a big mistake. Thanks, Jeff. So this should be a tau. Of course, we take the tropical variety. So I start with a system of linear equations in x1 up to xn, maybe non-homogeneous, with coefficients that depend on RT, as discussed. And then the corresponding tropical variety, I call that a tropical plane. Every subset of R to the n that comes this way will be called a tropical plane, and only those will be called tropical planes. So a tropical plane is the tropical solution set to a linear system of ordinary linear equations and n unknowns with coefficients in k. So then lines turn out to be trees. We've seen that in the plane. There was a sort of tree with 3 unbounded rays. Here's one with 4 unbounded rays. So a line in 5 space will look like this. We'll have 6 unbounded rays. Now what do we know about linear spaces? So a couple theorems. So the first one is an immediate consequence of this theorem. Well, that's a prime ideal, right? It's generated by linear forms. That's about as prime as it gets. So a tropical d-dimensional plane is contractible, that we know. It's a contractible polyhedral complex of pure dimension d. This is the important part. So it's of pure dimension d. A linear space, d-dimensional tropical linear space, has to be pure of dimension d. Now, this is very, very important. Very, very important, and that sort of distinguishes my perspective from that of my Russian friends. Most tropical planes are not complete intersections of tropical hyperplanes. Okay? In ordinary geometry, if you have a line in 3 space, it's always the intersection of 2 planes. Or if you have a codimension 2 linear space in 5 space, you can always cut it out by 2 hyperplanes. This is not true here. There are codimension 2 planes. In fact, in 5 space, you just take the dual to this. So this line in 5 space has a projective dual. That's a codimension 2 plane, and that is not a complete intersection. It's not the intersection of 2 tropical hyperplanes. That's very important. Pardon me?
Not even stably.
Not even stably. Stably, I think you're okay. Not even stably. No, I don't think you are okay, right, David? If you're in another far off in another component, I think even stably you're. Yeah. Yeah. I don't think so either. Yes.
I don't know what the most means here in most tropical planes.
Replace most by some.
Well, okay, eventually we're going to write down a parameter space for these things, and there will be open subsets of that.
Yeah.
Which
So
means it's not stable.
it's not stable. No, this is not stable. Now, there's another statement, right, that says, if you take intersections of tropical hyperplanes, what you get generally is not a tropical linear space, right? Because it need not be pure of dimension d. You can intersect these hyperplanes and get all kinds of junk. To be an honest-to-goodness linear space, you have to be pure of dimension d. Okay? So only very only those intersections of tropical hyperplanes that are consistent with this algebra qualify. And then, most of them, many of them are not complete intersections. So this most requires discussion. And then, as David says, there's a parameter space. So there's something called the tropical Grassmannian, and that parametrizes in a reasonable sense. It parametrizes the set of all d-dimensional tropical planes in R to the n, or d minus one-dimensional ones in tropical projective space. Okay. Let's talk about lines. That's a tropical space. I'm going to define it, actually. Let's talk about lines a little bit more. So I hinted at that already. So a line in tropical projective n-1 space is a tree. It's a tree with, and generically, it has n-3 bounded edges and n half-rays emanating into the n coordinate direction. So here's a line in 3 space. There's a picture of a line in 5 space. And we've seen, of course, examples in the plane. They are parametrized by the Grassmannian, G2n. And what's very nice, that was a very, very nice surprise for us when we first started this, turned out that the tropical Grassmannian G2n of lines in n space appeared in recent work, has been studied in the phylogenetics community. In particular, there's a paper by Lou Bellera, Susan Holmes, and Karen Folkman in Advances in Applied Math about 2 years ago, called the space of phylogenetic trees. And the space of phylogenetic trees equals the Grassmannian, G2n, with metric and everything. This is a polyhedral complex, and what they emphasize for biostatistical reasons is that this is has a metric, and has high symmetry, and it's exactly the same space. And here again, another cartoon of a line in 5-dimensional space. Let me fill this picture with life a little bit. Okay, so we've seen, so in Cinderella, right, we click on the screen, 5 points, there's a unique quadratic curve through it. So let's say we only click 4 points. So what can you say about the set of all quadratic curves through 4 points in ordinary geometry? So what can you say? What's the set of all quadratic curves through 4 given points in the plane? It's a line, right? Yeah? So there's a line worth of quadratic curves through 4 given points. It's a line in the coefficient space, in 5-dimensional space. It's a line in 5 space. So here's a picture. A picture I like a lot. So this is the line of all quadratic curves through 4 given points in the plane. Okay? Now, it's a tree, right? A line in P5 is a tree with 3 bounded segments, 6 lines, half-rays going off to infinity. So here it is. So these are all snapshots of the same 4 red points in the plane. So this is think of this as an animation. And each picture represents a point on a line in P5. And there you can see there's some 4 special points. So the 4 special points, they are the points where you have sort of a tripod, 3 guys coming together through that point. And that's the family. Here's a Gromov-Witten invariant. Okay, so how many singular quadratic curves are on this family? 3. Okay, there are 3. Here are 3. 1, 2. So a quadratic curve is singular if it's the union of 2 straight lines. Right? So if you have 4 points in the plane, then among the line worth of quadratic curves through 4 points, there are exactly 3 that are degenerate quadrics, namely unions of 2 lines. And here they are. So here's 1, here's 1, and then way on top in the middle, there's another one. Okay? So that's an example, sort of tropical geometry at work. A line of all quadrics through 4 given points. Pardon me? In the plane. in the through given points in the plane. Yes. Gee, I hope I didn't lose. Jeff, I think I lost one of your caps, you know.
It's on the other table.
No, not that one. Terrible. Okay. So, okay, quadrics to 4 given points in TP2. Okay, almost done. 3 more transparencies. So let me define the tropical Grassmannian. So the way to define these is always by the ideal, right? So we take the Grassmannian and its Plücker embedding. So let's look at the ideal IDN of algebraic dependencies among the d by d subdeterminants of a d by n matrix. So this ideal is an ideal in a polynomial ring in unknowns pi1 up to id called Plücker coordinates, and that's a prime ideal. And to make a certain point, I take it to be have integer coefficients. So this is a certain ideal generated by well-known quadratic relations called the Plücker relations. And we define the tropical Grassmannian to be the tropical variety of this ideal. Right? So how do we calculate it? It's the set of all vectors w in R to the n choose 2 such that the initial ideal is monomial free. Okay, that's what we're talking about. That's a subset of R to the n choose d. And, well, what do we know? It's a fan, right? That's Bergman's situation, because there's no t. Yeah, if you tropicalize these equations, you get a system of tropical polynomials, the coefficients, all the coefficients of which are 0. So there's no t. I don't see any t. So therefore, the tropical variety is a fan. The dimension is equal to the dimension of the Grassmannian, which is d times n minus d plus 1. It's the cone of the Grassmannian. This is the Kroll dimension of this ring if this z were k. But we can actually mod out, it turns out that this fan, all the cones in this fan have a common n-dimensional lineality space. So all the cones in this fan, they look like this. They have a common lineality space. And then we mod out that lineality space, and we get, and then we look at it on the sphere. So what we end up is, for the nicest picture, we think of this as a polyhedral complex on a sphere. And the dimension, it's a complex of dimension nd minus n minus d squared. Okay, so let me give you an example of a tropical Grassmannian that happens to be one of these spaces of phylogenetic trees. And let's go in slow motion. So here's an example. Plücker relations. So let's look at the ideal I2,5. So these are the algebraic relations among the 2 by 2 subdeterminants of an arbitrary 2 by 5 matrix. And there are 5 equations. They cut out something, namely the Grassmannian of codimension 3 in 10 variables. There are 10 unknowns. So this is the solutions to these 5 equations. These are the lines in 4-dimensional space. Okay, so now we tropicalize this. So now we apply either A or B or C in the main theorem, and we get the Petersen graph. Okay? So the tropical variety, the tropical Grassmannian, G25, in the simplified form that I described down there, is a one-dimensional object. Let's try. So 5 times 2 is 10, minus 5 is 5, minus 2 squared is 1. Okay? So it's a polyhedral complex of dimension 1, also known as a graph. And it's embedded on a sphere with all its symmetry, with its metric and symmetry canonically embedded, actually, I think in this case, on a 3-sphere or 4-sphere. And it turns out to be the Petersen graph. So in red, these vertices correspond to the coordinates. And this is the space of all lines, or in other words, the space of phylogenetic trees. So let's look at one of these components, so one of these edges. You can think of this as a project. I mean, this parametrizes all trees of the combinatorial type where 1, 5 is on one end and 3, 4 is on the other end. And then these are metric trees, 2 parameters. You can have this interior edge and this interior edge. They have a length. And as you so move up your mouse, so there's a second window, right? This is in one window, and then there's a second window over here. You click with the mouse and you drag along the blue line, and in the second window, the tree will change. And then as you get very, very close to this end point, then this little interior segment will have shrunk to nothing. And then there are 2 ways of restructuring this. So you can drag the mouse along the blue edges, and in the second window you have the corresponding tree.